Thank you very much to everyone for joining us for the June session of the Excellence in Breeding GOBii webinar series today. And we're excited to have two speakers who participated in the EiB Module 5 sabbatical program in 2019. Nahuel Soldevilla from the Integrated Breeding Platform and Santiago Diaz from the Alliance Bioversity-CIAT. Before we begin, I just wanted to let everyone know that we will be recording this seminar and make it available later for anyone who may want to access it. And during the presentation, if you have any questions, please feel free to share them through the chat window, or you'll have a chance to ask them directly to the speakers after they present. I will introduce each speaker before their talk, so I'd like to begin with our first speaker, Nahuel. He originally studied molecular biology in college at the Universidad de Buenos Aires, but later moved into software development and began working in that area in 2011. He gained experience at several different companies before joining the IBP in 2016, and he is now a senior software developer there. He has participated in several BrAPI hackathons, and today he will tell us about his EiB sabbatical work on developing a BrAPI compliant tool for field mapping. So Nahuel, if you'd like to share your screen, and we look forward to hearing your presentation.
Okay, thank you, Kate. Hello, everyone. I hope you can hear me okay.
Yes, thank you.
Okay. So as Kate mentioned, I work for the IBP, and last year I participated in the EiB sabbatical. This presentation is about BrAPI Fieldmap. It is a BrAPI compliant tool for editing field spatial layout using GeoJson information. BrAPI is a project that is an effort to enable interoperability among plant breeding databases, and it is a standardized RESTful web service API for communicating plant breeding data. And BrAPs are BrAPI-enabled applications. This is the BrAPI webpage, and this is where we can find some of the available BrAPs. The BrAPs are mostly visualization tools. We can see there are a lot of them. The idea of this sabbatical was to work on new BrAPs, and this sabbatical was hosted by Lucas Mueller at the BTI Institute. The Lucas Mueller lab is where most of these BrAPs come from. GeoJson is a standard for sharing geographic information. In the case of BrAPI, we can find GeoJson information in some entities like observation units, location, and images. This BrAPI heatmap is a concept tool that is not published yet. It is a BrAP for visualizing phenotyping data across plots in studies. The problem with this prototype is that there were no it was not possible to upload GeoJson information, or there was no tool available until last year. So that is why we came with the idea of creating a tool, a BrAPI GeoJson editor, to fill this vacuum and to provide a way to edit geographic information of a study. So we use BrAPI Hitman as inspiration, and some of the code was also reused in this new app. This app uses some libraries. Leaflet is a library for interactive maps. Turf.js is for geospatial manipulation of these GeoJson objects, and the tree is for other manipulation tasks. The initial development was done on the Cassava-based BrAPI test servers. But we started working on the breed-based servers, and later we integrated this BrAP into VMS. These two breeding system has some form of displaying the spatial layout of a study in rows and columns. This information will be used to retrieve the X and Y coordinates of the study that is necessary for this BrAP. I'm going to show this working as it was integrated into VMS. VMS has programs, and in this program you can manage studies. I have the study prepared, and we can see that this study has a layout. And now what I want to do using the BrAP is to display that layout in so the first thing that the BrAP does is it uses the location information from the study to position the map. In this case, the location is CIMET. Now the map has some tools here, and the way it works is that you need to specify where your field is located using a polygon tool, and after you do that, you are able to draw the plots on that area. So after you select an area, you click on load, and the plots will be lay out over that area, and the area is also used to calculate the length and width of the plots. After the plots are laid out, you can click over the field, and it make it editable, so you can drag it and position it. You can also right click over individual plots and adjust them. After you finish, you click save, and this information is uploaded using also one of the BrAPI APIs to upload information, and it is saved in the database. Once it's saved, you can, of course, open it again and edit it if necessary. So that is how the possibilities of the tool right now. In the future, it will also be possible to, instead of using this map server, which may not have the most recent images of fields, it could also be possible to overlap images coming from other sources, for example, aerial drone images. So that's basically my presentation. So thank you, and it's time for questions now.
Thank you very much for the presentation. Does anyone have any questions for Nahuel?
Yes, this is Tom Hagen. Can you hear me? Okay.
Yes. Hi, Tom.
Hello. Thank you for your presentation. It's very exciting to see this. You know, I have two scenarios. One is for a type of experiment or study that I would call a nursery, you know, where you're doing crosses to make germplasm. Those have fixed designs. And so that would work very well for what you've demonstrated. A type of experiment study that I would call a breeding trial typically has an activity called mapping, where you have to adjust the design array to the field space or area. And so the design coordinates change. And so you need to be able to generate your mapped coordinates. Do you envision adding that type of functionality to your software?
That is a possibility. Usually in breed base, for example, you can do this by using the available tools for plot layout. But with this new tool, it will also be possible to edit both the position of the plot and the geocoordinates at the same time. So yes, that is a possibility.
Thank you. Do we have any other questions from anyone else that's on the call or on the webinar? If not, I had a question. I was wondering if users want to be able to fit multiple trials or nurseries into one field, does the tool support that? Could you, after putting in that first plots, could you overlay a second set of plots around that within that same field?
Right now, you will need to redo regenerate the geographical information. So that it's not possible to I mean, if initially you have multiple studies in one field, and that information is available, all of them will be thrown together. So the important thing for the tool is the X and Y coordinates that are returned from BrAPI. So the app is not the only thing that is interesting for the app is the X and Y coordinates right now.
Okay. Thank you. Do we have other questions? Anyone else want to ask anything to Nahuel?
Yes, this is Tom again. Again, I think this is very good, and certainly for that type of experiment or study, called a nursery, this would work very well. Just from what you're showing here. So I think this is very good. But getting back to breeding trials, I realized that some of the things I'm asking are more complicated. So there may be a series of steps there that you may envision. So don't hear me. I'm not trying to say, oh, we should do this right now by any means. But breeders typically, like Kate was saying, have a set of studies, and it's sort of they're trying to figure out how to fit them into the piece of ground. So it's not something in advance. It's on the mapping side where you're doing that, putting together pieces of the puzzle and getting their actual coordinates, map coordinates. Also, people will add buffers and things like that. So you're in effect generating new plots that don't exist in your design array. And in a kind of a more complex example of this is what's called an augmented design, where you have a study that is just your performance checks, and you plant them in some type of pattern on your field, and then you fit in your test studies, around that. But you want though, and sometimes the term that's used for that final outcome is called a decision block. And you want, that overall array, inclusive of buffers that you've generated, captured and returned back to the breeding system. And they'd even add an additional wrinkle to it. Breeders don't always know where they're going, and so the breeding system may not be aware of the field or the location. And so, because breeders may be negotiating with farmers and whatnot to rent pieces of land. And so coming back to the breeding system, in addition to, buffer plots and mapped XY positions, may actually be the concept of what the field or location is. You're returning that location concept back to the breeding system. So again, I think this is an excellent starting point, but there's a series of potentially next steps here that particularly for actual breeding trial operations would really add a lot of useful capabilities.
Yeah, I agree. So this has, I think it has started as just a way to update this geographical information, but it can evolve into something more, a way to integrate all of those needs to create more complex design using the map instead of a table with box that you can drag around. It's more easy to use a map instead of a table. So I think this tool has the potential to do that.
This is Tom again. Another scenario that, say you've done all I've described, you now in your breeding system have, you've gone from a design array to a mapped array. And that certainly could come to your software. Have you thought about, breeders now are assigning packages of seeds to these mapped plots, and use the seed package array assignment to lay out planting operations. Have you thought about perhaps some functionalities where you could use what you have here to facilitate planting? And then another very useful scenario of what you have here is people need to understand when they go, to have a guide to where to go to, say, collect a sample for genotyping, or where to go to collect a sample for some phenotypic traits. So anyway, I'm just see a lot of potential here, and I just wanted to raise up to you, some potential future steps.
I'm sure. I think the BRAP there is a this application is on GitHub. You can find it on Genomics BrAPI Fieldmap, and I think it isn't in a beta state, so maybe as we discover all of these features, we can get all of them together and see how we can evolve this tool into something more complex. But I'm not sure if combining a lot of features in the same BRAP, maybe it could end up being too complex. But it certainly is a possibility.
Thank you. And I think in the seminar series page, we have posted the links to GitHub. I can also put it into the chat before the end of this meeting. But thank you very much for sharing this exciting tool with us. Since we have another speaker as well, I think that we may want to move on, but does anyone else have any other final questions before we move to Santiago? Okay, if not, then thank you very much again for sharing this.
Thank you.
Cool tool with us. Okay, so the next speaker I would like to introduce is Wilson Santiago Diaz. He studied agricultural engineering and vegetable production at the Universidad Nacional de Colombia, and after graduating in 2016, he took a position at CIAT, the International Center of Tropical Agriculture, where he is a research assistant of the bean breeding program. He gained experience working in genetics and data analysis of traits related to biofortification and seed quality in common bean and their applications in breeding. Today, he will tell us about his 2019 EiB sabbatical work on genomic prediction in beans. So Santiago, if you can please share your screen, we look forward to your presentation.
Thank you, Kate. I don't know if you see my screen now.
Yes, thank you. It's coming in clear.
Okay. Thank you, everybody. Thank you to EiB for this opportunity. Let me tell you, my sabbatical project was in CIMIT Biometric and Statistic Unit in Mexico, with the aim of learn about genomic prediction under the guidance of Dr. Jose Crosa. Moreover, to have the opportunity to observe the application of these tools, mainly in genomic selection in the cross of in CIMIT words, such as maize and wheat, and all this with the final objective to bring in this knowledge, the experience of the CIAT bean breeding program, and we take up first steps with this new strategy in the breeding world. For this reason, I titled my seminar Genomic Prediction for Agronomic Traits in Common Bean and Their Application in Breeding. This work is directed by Dr. Boderaz, and in which several collaborators have participated. In this seminar, I like to show you the results and the advance that we have obtained so far in this theme. Okay, the topic that I will briefly discuss in this seminar are theoretical basis of the genomic prediction. I want to show you some results in genomic prediction in some trials, evaluating yield trials, seed quality trials, the ongoing implementation of genomic selection that we have planned for the near future, and the outlook and perspective that we have for this study. Okay, I want to start with this picture. Genomic prediction is a tool that can predict a plant genetic merit based on the scoring DNA marker. This is interesting, for example, because genomic prediction can predict how a plant progeny will perform before the traits are measured without needing any other information, or on predict additive effects in early generation of the breeding program generation, such as F2 or F3, to achieve a rapid selection cycle with a short interval. Genomic genomic prediction combines molecular and phenotypic data in a training population and uses statistical models to estimate the breeding values, the GOBIs, of individual in a testing or validation population that have been genotyped but not phenotyped. Later, we can evaluate the precision of these models fit by the training population data, comparing the phenotypes observed in the field with the phenotype predicted by the models. Later, we correlate this data, and we perform this procedure several times, alternando individuals for the training and the validation population to obtain more robust data, in this case, of prediction accuracy of these models. In this way, we begin to develop our prediction work. Now, I want to present you this study about genomic prediction that we developed in our work group. In this study, we wanted to evaluate the prediction accuracy of the genomic prediction models in agronomic traits of common bean under abiotic stress. The population used in this work was the BEF panel. The population used is a bush Andean bean population. This population is very important for our breeding program because it was made up of elite genotypes development and CIAT that present interesting characteristics and traits sobresalient in different traits like stress drought, biofortification with iron and zinc, and other traits. For this reason, this population is continually renewed and new genotypes are added in each trait. In this work, measure 4 traits: days to flowering, days to physiological maturity, seed weight, and yield. And these traits were evaluated in 2 different locations: Palmyra, under drought and irrigate conditions, and Darien with different levels of phosphorus. In this picture, you can see the high phenotypic variability that appears in the different trials in all traits evaluated in this study. We also evaluate different statistics models to see if there is a difference between the prediction ability in each of the models, and we compare the results with the prediction data of another population. The magic population, a multiparental population developed crossing a set of 8 Mesoamerican breeding lines from CIAT. Here we can see compared prediction data for yield that no difference is observed in models used in both populations. You can see that we work with different models, Bayes A, Bayes B, Bayes C, Vilasov, and you can see that no difference is observed. Only there are differences to prediction ability between populations with best panel to the left side and to the right side for magic population. Okay, we also want to evaluate the minimum number of markers necessary to perform the prediction and its effects of the prediction ability through two methods. Randomly varying the number of the markers used, and the other strategy was using different LD thresholds and some 3 minor allele frequencies, and we found that in our case, at least 2,000 markers are enough to obtain a more stable prediction ability. You can see in this picture that curve of the prediction ability is stable. Later to use a minimum 2,000 markers. Okay. Later, we analyze the different size of training population and its effect of prediction ability. Here on the graph, we found that using the training population size greater than 50%, the prediction was stable in both populations. In all traits, you can see here, here, and here that the curve is stable in this part. Regardless, the both populations have different number of individuals. Is the same, similar in the two populations. Regardless, for example, the magic population have 600 individuals, and the best population have only 400 individuals. Now we are looking at the cross-validation data for each of the trials conducted in the both population. It's interesting to see how in the traits that we know are controlled by few genes, such days to flowering, days to physiological maturity, they present a higher prediction ability with an average between 0.5, 0.75. However, the complex traits such as yield and seed weight, that prediction was more low, with an average to 0.3 and 0.6. This is a trend that was observed in both populations. It is also interesting to observe how the prediction, the precision prediction, was affected in location of variant. This graphic is the box plot with color red, in which the poor prediction is a lower prediction result we're seeing. This may be due to the lack of replication used in the field. We could say that was a low quality design experimental in this location. Another important highlight that was observed was the correlation between heritability, the broad sense heritability, and the ability prediction in all these traits. You can see there are a correlation between the broad sense heritability with the all traits in prediction. Now, our next objective was try to predict a trial using the data from past trials. I mean, for example, we use the information for Palmyra 2013C to predict the trial of Palmyra 2014A. This is called Model 1. The Model 2 trial to predict the trial of Palmyra 2014C, combining the data from Palmyra 13 and Palmyra 14A trials. And so on, we feed the models with information from past trials to predict the current trials. Here is interesting to observe how the prediction ability increased as the models with the more tests are fit. The models with more fit, with more data, with more trials, increasing the prediction ability, but only see a drop in the prediction when we try, for example, predict the trials carried out in Darien with the trials carried out in Palmyra. It's interesting to see the drop of the ability prediction when you try predict one location with other different location. This information and this data and more details of this study you will be able to consult soon in Frontiers. But in other studies, more simple, in this case, we examine the prediction in other traits, in this case related by accumulation of iron and zinc. That is important key target in our breeding program. And you can see evaluate different models. In this case, there are not a difference using the different models, but there are a difference using the different population. For example, we use in this case BEF and MAGIC population, but these results is interesting because we have a high data precision predictions in a trait that is a very complex trait such as zinc, iron, and zinc content. Other interesting example is a prediction in another kind of traits like seed quality traits. In this case, you can see cooking time and water absorption capacity. And we evaluate, in this case, 4 populations, the BEF and MAGIC population that I showed you before in this study, and other 2 populations, in this case, MIP population, that is a Mesoamerican breeding panel, and G4G. G4G is a biparental population, very interesting in analysis studies genetics in bean. Okay, now I try explain more what is the plan in the near future for this strategy in our breeding program. Normally, the generation cycle normal is in this case in a hybridation event, the crossing 2 or 3 parentals, and we advance the lines to F7 of F6, and in this point, these lines return onto other event of hybridation, and consequently is the generation cycle normal in our program breeding. But with the implementation, we will want, we will hope generate a cycling of generating of new lines of new varieties more quickly. In this case, with the implementation of GS, we hope select the lines in early generation of these lines, for example, F2, F3, and choose selecting these lines and turn on in selection of hybridation and advance these lines consequently, and can we genotype these lines in F6 in different stages. I want to present our first population that we try implement the tools of genomic selection. This population is called population 129, bush nutrition. Our goal in this nutrition are very interesting. The goals on a bush is a bush population, but we expect that bush population we have biofortification individuals. In bean, this is hard because there are, you can see in this graphic, there are negative correlation between yield and iron concentration. Allow lines, allow genotypes have these characteristics because it's important, but it's a difficult have. But we have another goals, like such as resistance to some disease, fast cooking, and early maturity. In this case, we feed our models with an index selection that have, for example, the models, the statistical models of genomic prediction that we work in the BEF population, the statistical models of prediction in cooking time using 2 or 3 populations, statistical models of iron in 3 different trials in 3 different locations, and the marker data for mass in this disease, ALS and BCMB. And for the moment, our preliminary results there are. Here you can see the genomic prediction of 800 individuals F2, F3, and you can see the normal distribution in these traits. The data is normalized, and you can see the first step on our breeding programs to start to advance in this strategy. And our outlooks on CIAT, the implementation not only in CIAT headquarters in America, only take the information and take out for Africa, for the other sectionals in Africa, and generate more information for retroalimentation, retrofit in the ED data for the genomic selection of the bean breeding program. Thank you.
Thank you very much for that great presentation. Do we have any questions from anyone in the audience in the webinar?
Yeah, thank you for your presentation. I am Secure by name. So the question I want to ask is on the 2 population you use in your study. So I just want like a clarification. So I was thinking the magic population and the magic population will have low ED compared to the VEF population.
Okay, yes. In this study, we prefer the BEF population because it's a breeding population in this case, but we won't compare these results with the prediction data with another population, another population that we construct in another case. In this case, is the magic population. In this case, you can see there are differences in the prediction data, in the prediction ability in both populations. The BEF population present higher correlations between the models, but it's interesting. It's interesting because in the both population present similar parameters to for create the models. I know if answered your question.
Yeah, so that actually kind of answer it, like the kind of when you're using the same size of marker size.
Okay.
So, because of, I expect magic to have low ED and VEF to have like high ED. So, of like using the same set of marker for that comparison might not actually work, because like the matching population would definitely require very large number of marker to be able to track the QT as a grading within that population to have a good prediction. And at the same time, when so why I'm asking this question, because I actually do a similar study in my PhD program.
Okay.
Yeah, as well. So that's kind of like observation that I have. And at the same time, size of the training set at the same time, the size of the testing set when you're making Pearson comparison also like have an effect.
Mm-hmm.
I don't know if you observed that.
Okay. But I think that is necessary because, for example, in this case, we have different threshold of LD. For example, we examine a set of markers in both populations with LD lower than 0.3 and evaluate that is the estimate of prediction ability in this case. And it's interesting because if you see the line white in this graphic is the curve result of choosing a different number of markers. But the point, the box plot, the minimum box plot with colors is choosing the threshold with LD. And you can see, for example, in the magic population is lower than the is lower than using a number of markers punctually. But in the other population, the BEF population, using the different threshold of LD, appear can we have a higher prediction ability in this case to compare that number of markers.
Yeah, you're right. Trying to drive out is so what I'm trying to drive out was the difference in the AD pattern between the two population.
The difference between prediction ability.
Yes, actually, what is driving the prediction accuracy?
In this case, we hypothesized. Now we don't sure in this case, but for example, we can say here, for example, that difference in the structure population. In this case, the BEF population is a natural population. This difference of the structure population, it can be incidence in the prediction ability. Another idea that we have is, for example, if there are difference in the experimental design in field, can be incident in the quality of the data. Yeah. For example, to obtain the blobs that is important to estimate the prediction ability. But for the moment, it is ideas. For the moment, not is confirmed this hypothesis.
I see. Yeah, thanks. So the other question is, so when you predict using the historical trial, so do you combine the historical trial plus the recent trial, or you predict the new trial directly using the historical trial?
Yes. Yes, in this case, when in this first part, the internal cross validation in this graphic only use the same trial to predict the same trial. Is the cross validation type 1. By the cross validation type 2, in this case, yes, like you say, in this model, we try combining trials, historical trials, to predict the actual trial, and we try become a robust model with the advance with different trials. For example, in the last trial of 2018, the training population was the all historical trials performed used in the study. But I think it's important, for example, the phenotypic correlation that we evaluate too. In this case, you can see the green line. The green line is the phenotypic correlation between the historical trials with the actual trial. And you can see that there are a correlation between the prediction ability with this correlation phenotypic.
I see, yeah, that makes sense. Yeah, thank you.
Thank you to you.
Thank you. Do we have any other questions for Santiago? Okay. Well, if not, I would invite Santiago, if you, when you have a link for the publication that describes some of this great work, if you share it with us, we can also post that on the EIB webinar site to share it with others. But I would like to thank again our two speakers today. I hope that they enjoyed their EIB sabbaticals. They obviously both got a chance to do some great work here. And I'd like to just let people know in July, we'll be having a presentation from DART about a tool for curating genotypic data. And then we have other presentations coming up after that, and we'll hopefully have a second round of speakers from the EIB sabbaticals in fall, likely in October. So thank you very much again to our speakers, and thank you to everyone for presenting, for attending today. And be well, stay safe. Have a good day, good evening.
You too. Bye.
Thank you, everybody.